Okay, welcome to the unit on area and volume. This unit's going to be some stuff you've seen before probably, but it's going to probably involve more trig than you used to using. The first chapter in the book, so this covers chapter 11 and chapter 12 in the book. And the first chapter 11, is all about 2D area stuff. Oh, wait a second. I think this is oh no, this isn't wrong. It's just this also covers 11.3 today. I added that this year because that's what 11.3 is about. And then chapter 12 is all 3D stuff. So we just put them together in the same unit because they're very closely related. Okay, so here's a bunch of area formulas to get us started. I think these are probably the ones you have seen before. Notice in a lot of these area formulas there's a multiplication going on. Multiplication's an area because the basic idea of how area works is like rectangles or rhombus and squares. You're probably used to rectangles and squares first. When you multiply things that are at 90-degree angles, that's basically how area is defined. Area is defined as these square units, right? And how many square units fill up the thing. And I guess this is the first time, and that's kind of the newish kind of principle here, is that direction times that direction is what gives us the area of the stuff inside the thing. So most of the time so I guess as a general hint, when you get stuck or when you're kind of intuiting things, that there's usually going to be some kind of multiplication involved with area. Notice that the units that we're going to get on area is going to be, it's like centimeters squared or inches squared or something like that. We're talking about something that is 2D, so it's a two-dimensional area measurement. And the things that you multiply, generally speaking, are going to be found at right angles. And that's going to continue on into the volume unit. Okay, so I don't know if I need to talk about all these. You probably heard about these before. Parallelogram includes rectangle, rhombus, and square, but it's base times height. So if we were talking about a parallelogram here, the height of the parallelogram is measured that way. And that times the base is the same as a rectangle that has the same base and height. Rhombus also works that way because it's a parallelogram, but I'd have to be talking about the height like that. Triangle, I'm sure you've seen this one before, but again, we mean height and base. Well, I shouldn't label it there. I mean height and base that are perpendicular. This is really small. Height in here and base in here, so that those things are perpendicular. This is all explained on that column on the right here. Rhombus or kite. In class, I can kind of tell you the why behind all of these. Oh, let me write that. Let me write this kind of over here. I'll do that when I do the video. Why are all these formulas the way they are? And I can break it up. Basically, they all break up into rectangles of equal area of the original thing you see. So rhombus or kite. Why don't I draw a kite? I've already drawn a rhombus. So imagine a kite. Kind of looks like this. Diagonal 1 and diagonal 2 are like this length for D1 and this length for D2. And notice those would be at right angles again. Like this entire length is D1 and this entire length is D2. Okay. Trapezoid you've probably seen before, but there's some wonderful explanations and visualizations of why that is the way it is. Okay, I've been yapping too much. Okay, so find the perimeter and area of this whole thing. We'd never really talked about perimeter, but we have talked about perimeter before in like last unit. So I'm going to fill those in. I got this 25 from Pythagorean theorem. Hope that wasn't too much of a surprise. Perimeter is simply add up the when they say figure, they mean the solid line figure. Add up all of the sides, and that is, I don't know, 98, looks like to me. Area, though, we're going to use, and I've been talking about this since last unit. When you use a formula, let's see the formula in variables. That's going to be 1 point on a quiz or test. Let's see those variables replaced with values. So the base here is 23, and the height is 24. Oh, no, I need a calculator. Okay, in my calculator, I realized that, first of all, this was wrong. This is at 98. This is 96. Okay, and then 23 times 24 is 552. So this is 552. I should technically call this units, and I should call this units squared, so we have that designated differently. Okay, of the given triangle, so that means this triangle, the one with the bold sides. So perimeter, I'm just going to add up the three sides. Okay, so I need this side. Well, I don't have that side yet. I can get that side as the hypotenuse of this little right triangle, but I don't have all the sides of that little right triangle. So I got to get this side first, which I can get if I apply Pythagorean theorem to the overall big triangle picture here. So 19 plus 27, that's 46. And then with a little Pythagorean magic, I get that x is the square root of 1605, which is approximately 40 and some extra. Some people are doing these things wrong on the. I guess we had some Pythagorean theorem in the circles unit because we had radii perpendicular to things. People just put the hypotenuse in the wrong place when they were doing right triangle stuff. Remember that the hypotenuse is supposed to be the longest side. So yeah, this thing turning out to be 40 point something is fine. I'm gonna fit that in there. Now I gotta find this one. Let's call this y. So now I know that x squared plus 27 squared is going to equal y squared, and that means that y is about, well, it's the square root of 2334. I'm trying to save video time by doing that off camera. All right, 48.311. So now I have to add this up. Perimeter is that plus 19 plus 61. So that answer I just had plus 80 is 128.311. And those are just regular units. And then area, I'm going to use the formula over here. I'm going to use half times base times height from the last page. Half times, now the base of this triangle is 19, and the height of this triangle is going to be whatever x was. X was the 40 point, excuse me, 40 point whatever thing. I can write that here, 40.062. Then from my calculator, I take that number, 40.062 times 19, and divide that answer by 2. I get 360 point something. And I should call that unit squared. Okay. Yeah, every triangle has 3 sides that I could use as the base and another thing I could use as the height. Like there's an altitude always to that side. So the one that I saw pictured there was the 19 and the x. We should do a trapezoid because I haven't had a trapezoid yet today. Like I might save this one. I can tell already. I'm going to save that one for video. Okay. It's not just another triangle, but it is more interesting because it's not pictured. All right. So area of the trapezoid formula I'm going to use here is a half times base 1 plus base 2 times the height. That may look a little different than the last page, but it's equivalent. And then, because one reason to have these formulas written out is it kind of helps you know, like, where am I headed? Like, what are the ingredients that have to go into this recipe that I need? And 51 doesn't go directly in here, but 51 is going to help me find this height. I can think of this height as being right here, and I have part of a right triangle right there, where this segment there would be 13, so I know that this part that's left over is 4. I need to find the height of a triangle with a 51-degree angle and a leg there of 4. So the SOHCAHTOA process I'm going to use here is going to be tangent. Tangent of 51 is opposite over adjacent, so this is 4 times the tangent of 51. I guess I could write that here so you could know what I was doing. And that whole thing is, pause, 60 times the tangent of 51, which is equivalent to 74 point something. What's tricky about these, and this is just unit squared, back up here I remember I was saying, like, you can kind of know whether you did this right because it should be, you know, less than 61. This one down here, like, you get this answer of 74 point something. It's kind of hard to know, like, is this at all, like, reasonable? Yeah, so because they didn't give you the height, we found a height. I never really found the length of that height in a decimal form. This is about 5 point something, 4.94 it looks like. So you can kind of estimate that this trapezoid is probably going to be less than 17 times 5, and 17 times 5 is 85. So we're kind of in the neighborhood of that, and so yeah, maybe this is right. But some of these are really hard to estimate, especially when we get into the 3D. So I encourage you to try to estimate your answers for reasonableness, or kind of like look them over one more time and go, that seems like it might be. But once we get into surface area and stuff, it starts to get really hard to do that. So as much as possible, I think it's a good idea. All right, area of a rhombus and kite, I'll do one of these. I want to say that the example 6 is more like 4. So I'll do 6 on video, and I will do 4 in class. So let's go to 6. Yeah. So I want to find the area of this kite. So the area of the kite from the other page is d1 times d2 divided by 2. And those things are this length and this QS. So it's really like PR times QS divided by 2. I can do it that way, or really I could chop this thing up into triangles and do the 2 triangles. I don't know which one's actually easier. The 2 triangles might be easier. It's not too bad. I'll do it. I'll use the formula the way it is. Okay, so I need to know the lengths of these diagonals. One of them is already given to me. The QS is 20, so that's lovely. So I just need to find this length from P to R. P to R is going to come in two parts. I'm going to find that part first, and then I'm going to find this part. The part on the left is easier. This is a equilateral triangle. So these triangles here are 30, 60, 90. So if that's 60, so this, first of all, this is 10 and 10. That's half of this side of the triangle. And so the part in here is 10 root 3, if you remember your 30, 60, 90 rules. So that part's 10 root 3, that's not so bad. Then in here, I have a right triangle with a side of 12 and a side of 10. So to find this little piece in here, I need to do Pythagorean theorem, where 12 is the hypotenuse, and figure that out. This is the square root of 44, so I'll leave that for now as that. And then what I'm looking for is PR. Well, PR is the square root of 44 plus 10 root 3 times 20 divided by 2. As an exact answer, I can kind of call this whole thing 10 times this. And that's really about as good as it gets exact-wise. But if you wanted a decimal approximation, I get 239.538 units squared. All right, this is the last part. This is about circles. Area of a circle is pi r squared. Probably not a surprise. You've probably heard that before. But anyway, this is the time in the book where we finally start using that. Pi d squared over 4. Like you really don't need to know that one very much. Like I wouldn't even memorize that. Pi r squared, though, is pretty standard. That's the way most people are going to do area of a circle. All right, area of a sector. So by area of a sector, we mean the area of this part inside, like just that. We're going to find that the same way we found, this sort of the same trick that we found length of the arc. Remember we did length of the arc like that? We did a fraction out of 360 for the degrees. We're doing the same thing here. So this is just, and there it is. It's the fraction out of 360 that angle is times the whole area of the circle, because it's that proportion of the area of the circle. Pretty intuitive to come up with that. All right. Calculate the area of a circle with diameter 6 centimeters. So the area is area formula, pi r squared, pi times 36. We usually write that as 36 pi, and these are units squared. All right, a 6-ounce oh yeah, I hate this question. We're gonna do this in class. I mean, I don't hate this question, but it's gonna take too long to explain. Let's do 3 together though now, or watch me do 3 now. In the given diagram, the area of the sector is 63 pi over 2. So this thing is 63 pi over 2. So the formula at play here is that the area of the sector, oh, and I like to put a little subscript for what it is I'm talking about. The area of the sector is a subscript. It's a sector. Area of the sector is x over 360 times pi r squared. And I know I can replace this value with 63 pi over 2 equals 140. I'm supposed to find the radius. So I'm trying to find over 360 times pi r squared. Now I just got to do some algebra. Well, take the pi off both sides. That's kind of nice. Oh, do I have can I just like cross these things out? Okay, those are crossed out. And then cross out some more stuff, such as I can reduce this fraction pretty easily. I can divide some stuff by 2. Like, there's a lot I can reduce. I can call this 7 and 18. I can call this 9 and 1. I think that, I can divide both of these by 7. I call that 9. And so now I end up with, just what's left. 9 equals r squared over 9. I believe r squared equals 81. Or in other words, r equals 9. Gosh, I hope I did that right. Let me check. In fact, I did. That is actually 9. And those are 9 units, whatever they are. Great. And the area of the circle, well, now that I have the radius, this is pretty easy. Pi r squared. And so area is pi times 9 squared, which is 81 pi. And those are units squared. All right, last page. Find the area of the shaded region. Given this, okay, which one would I rather do here? I think I might why am I still writing with my finger when I try to scroll up? I think I might rather do 5. We'll do 4, and we'll do 4 as part of the warm-up in class. But I'll do 5 now. Okay, find this shaded region. This is called a segment. Oh, notice how I wrote this. Don't do that now. Do that in class. I need to find this thing. This shape is called the segment of a circle, which is a terrible name for it. We have other uses of the word segment. I don't know why they define that thing to be a segment of a circle. But that's kind of the standard way to do that. So one way we're going to do segment, because they don't give you a formula for segment in these notes. One way to think about segment is, let's do area of, and I'm going to do my little subscript thing here. The area of this shape equals the area of this shape minus the area of the triangle. Hopefully that makes sense. If I take the sector minus the triangle, I should get the segment. So the formulas for these things are x over 360 times pi r squared minus half times base times height. Okay, so that tells me what I need. Well, it's 140 again, like last time. Why do we like 140 so much? Okay, times pi, well, at least I have radius this time. It's a slightly different circle. Minus half. Okay, now I need the base and height of this triangle, because this is what I'm subtracting off here. So these are both 8. That's great. This is 140. Well, let's take that 140 and let's chop this into 2 right triangles. So that makes, if we make a right triangle here, this is 70. And really what I care about is this thing here. I don't know if you can see that, but I called that x. That's half of AB. So x is part of a right triangle with a 70 and an 8. I think that's going to be 70. I'm thinking which part of SOHCAHTOA. X is opposite, so let's do so for sine. Sine of 70 is opposite over hypotenuse. So the whole thing, AB, is going to equal 16 times sine 70. I'll write that over here for now. So the base is 16 sine 70, and the height is, oh, I didn't find the height. The height, this little thing right here, is, I could do Pythagorean theorem with this, or I could still use the 70 and use SOHCAHTOA. I could say cosine. Cosine 70 is adjacent over hypotenuse. So 8 cosine 70 equals h. 8 cosine 70. Okay, you might think this looks really gross, but this is actually quite typical to have sine and cosine of the same angle show up in one of these things. Okay, I'm gonna do a lot of heavy calculation. I'm gonna pause through this because this video is getting long. You might want decimals for these separately, because if something goes wrong, like I know this first part should be bigger, right? Like, yeah, that 224 pi over 9 is this. The second part is 10 point something. Like, I know that should be considerably smaller, so this kind of helps kind of reinforce my thing. To find this final answer, though, I'm not actually subtracting these rounded decimals. I subtracted from these exact answers on my calculator to get this one down here, this version, which is 67.9061. So I could just do that. And of course, these are units squared. Okay, I think that's all for this video. Don't do any of this work yet. We're going to do that in class. Okay, I'll see you then.